All right, Trunkel here again from Honor Lab. I'm going to show you the electron diffraction experiment, which is something that you're going to do while you're taking data over here with the X-ray machine. So while you're sending X-rays at a crystal and this is collecting data automatically, you're going to be working with this equipment during week 1 of the experiment. All right, so what we have here is a power supply connected to our electron diffraction tube. This tube is very expensive, as Dr. Mulhall found out when he first arrived here at the U. It's a separate story for later. Okay, so essentially what we're going to do, we're going to take electrons and accelerate them at a very high voltage, and it's going to strike a powder of graphite. All right. Now, when those electrons bombard into that powdered graphite, they're going to diffract off at certain angles. So what we're going to see here are rings that are produced on this white screen. Okay. If it were a crystal, we would see spots. But since it's a powder, we're going to see the entire ring pattern lit up. So this is what we're going to do first. You're going to go ahead and turn this guy on. And if you would hit the lights, please. All right, we're going to start at about 2.5 kilovolts. All right. So that's 2.5 kilovolts, 2,500 volts. And as this thing warms up, what you're eventually going to see is you're going to see a ring pattern showing up. Actually, I'm going to have, just if you could block the light coming from the lab. There you go. That's perfect. So you might have to start, you can kind of see that the rings are there. What I suggest you do, you're going to eventually be taking pictures of these rings. Try to get as high a quality picture as you can. So watch what happens. As I increase the voltage higher and higher, you're going to see the rings start to get smaller and smaller. So at the higher voltages, you can easily make out the ring patterns there. Now this is what you're going to do. You're going to put something near these rings of a known width. So here I have a very small ruler. So we know what the width of this ruler is. So you're going to put that somewhere near the rings. And what you're going to do is you're going to snap a picture of the ring pattern. And you're going to get one picture every time you change this voltage. So you're going to start down here at 2.5 kilovolts. Take a picture of the rings with something near it so you have a reference. And then increase it at 0.5 kilovolt increments. Take a picture with something that you know of a known width, and then continue up to 5 kilovolts, 5,000 volts. All right? All right, you can put the lights back on. Now, after you do that, there's also something else we need to measure here. So we need to measure the distance from when the electrons are coming out of this tube to the screen. So what you're going to have to do is take a picture of this side of the apparatus with something else that you know here, and get that picture. Now what you're going to have to do is analyze those pictures with a program called Logger Pro. So if we come on over here, Logger Pro is installed on this computer. So it's right here on the desktop, Logger Pro. So I have it open already. So this is a program that allows you to import a picture and then determine distances given something that you know has a known distance in the image. So I'm going to go ahead and do Insert, Picture, and then Picture with Photo Analysis. So did you get me doing that? Okay. So you find your picture. I have one example here. All right, so we're just going to bring it up so we can see it. All right, so you can see I have my known object here. I got my 2 rings, and I have the center here. So this is what we're going to do. First thing is you're going to hover over this icon. It'll say Set Scale. What we want to do is click and then drag. You see that it's creating a line here. I want to click and drag to the length of my known object, and it'll ask you to import a distance. So I know this to be 11 millimeters. I just made that number up. You're going to actually have to measure that thing if you use that ruler. But let's say it's 11 millimeters. You put that in here. All right. Now, basically what you're doing is it's calculating the distance per pixel in the image. So now I could set an origin using this button, Set Origin. So I'm going to put it to the very center of my rings, which should be the center of the bright white spot here. Okay, so now I have an origin set, and then this button here, Add Point, will allow me to calculate distances referencing that origin point. So if I go to the center of my first ring here, I'm going to click there, and then it'll give me that distance. So it's telling me the radius of that inner ring is 11.59 millimeters, and you can click the center of the outermost ring, and it tells you that that radius is 17.89 millimeters. Basically, using the calculation, it's determined for how big each pixel is distance-wise. So you're going to do that for each of your pictures to get the ring diameter at different voltages. Now, Majid, if you want to come back over here, I have a little cheat sheet for them. All right. So if you go on the website for this tube, So, sorry, Majid, I'm going to get in your way again. All right, you're going to look on this, I'm going to have you do this as exercises. Sometimes when you do an experiment and you don't know something about the equipment, you have to go on the manufacturer's website, so this is a good thing for you to do. So this is a TEL 2501 universal stand. So if you go to there, you're going to find the link to the actual tube on the website. So it's going to give you some information. It's going to show you pictures of the geometry of everything, which will be useful, but this is essentially what you're going to try to do here. You're interested in figuring out the wavelength of an electron. All right, so what you're going to do is you're going to start by doing the conservation of energy. Essentially, you're going to have all of the electric potential energy converted into kinetic energy of the electron. And along with these de Broglie relationships for wavelength and momentum, you can combine these equations here, and you're going to end up getting something like this when you evaluate all the constants. All right, so you're going to need to get to this point in your lab report. If this is the experiment where you're writing your report, you need to derive this equation, because this capital V here is the accelerating voltage that you're going to be recording from the power supply. That's going to give you lambda. So in terms of this graphite powder that we have here, we're interested in determining the atomic spacing of that powder, of what it's made out of, the graphite. So that's relationship is lambda equals d sine theta, where d is the atomic spacing that we're looking for. So what we're going to try to do is get a lambda, all right, and an accompanying sine of theta, which you can get from the geometry of the device, which you'll find very nice pictures on the actual website for that electron tube. And what you're going to do is you're going to get ordered pairs of lambda versus whatever sine of theta equals, which is going to be related to d, the diameter that you're recording out of data, or the data logger software, and L, the length from the electrons are emitting to the screen. And you're going to make a plot to try to determine what d is. All right, so Majid, if you want to just get a good picture of that, so they can stop the video if they want to look at this paper at any time.
Because de Broglie was such a good physicist.
Wasn't he good?
Right.
Wasn't de Broglie good?
Right.
All right, well, that's one of the experiments you're going to do during electron diffraction and X-ray diffraction while you're taking data with the X-ray machine. See you later.